So coming to the general introduction, there are generally two methods that are going to solve the indeterminate problems in structure analysis. So one is force method and another is a displacement method. So for any linear elastic structure which is subjected to a prescribed loading, these two methods are generally used, but their approaches are different, but they give the same results in terms of force and displacement response. So these are some of the differences between the force method and displacement method. So coming to the first, the unknowns are redundant forces in force method, whereas the unknowns are displacements in displacement method. So type of indeterminacy is static in force method, it is kinematic in displacement method. So firstly, you're going to identify degree of static indeterminacy in force method, whereas in displacement method, degree of freedom is identified. So in the force method, the compatibility conditions are adequate to solve the unknown forces, and these compatibility equations are based on displacements. Whereas coming to the displacement method, equilibrium conditions are adequate to solve for the unknown displacements, and by using these, you are going to get the displacement equations. And here we are going to get the force response directly after solving and finding the unknown redundants. Whereas here we are going to find the desired force response after solving and finding the unknown displacements. In both these methods, you are going to use the principle of superposition. In force method, it is used with respect to the forces, whereas in the displacement method, it is used with respect to the displacements. Some of the methods related to the force method are Betti's theorem, column analogy method, conjugate beam method, and flexibility method. Whereas the methods related to displacement method are slope deflection method, moment distribution method, Canis method, and stiffness matrix method. So with this initial introduction related to the different methods that are used in the structure analysis, we have taken slope deflection method. So this is related to the displacement method. And here in this method, the unknowns are the displacements only. So coming to this slope deflection method, it was introduced by George A. Maney in the year 1915. Here it is generally ideally suited for analysis of indeterminate beams and rigid jointed frames. And it accounts for the flexural deformations but ignores the axial and shear deformation. And here the unknowns are rotations and relative joint displacements, that is theta and delta. And for the determination of the end moments of the member at the joints, this method is general, requires the solutions of the simultaneous equations that consisting of rotations, joint displacements, stiffness, and length of the members. So the development of these methods in the matrix form has led to the stiffness matrix method, which is commonly used for the analysis of large structures with the help of the softwares. Here some of the assumptions are there. So first assumption is that all joints are rigid. That means the angle between any two members of a joint does not change even after loading. Here, if in these two figures, you can just see the angle between AB and AC. So theta. So in the figure A, it is a theta before deformation at the rigid joint. Similarly, at this joint only after deformation also it is getting theta. So that means the theta is going to remain even after deformation also. Coming to assumption 2, the distortions due to axial deformation are neglected. Similarly, you can see here the axial deformation is neglected here. And next, assumption 3, the shear deformations are also neglected. So here the assumptions are shear deformation and axial deformations both are neglected. Why? Because they are generally considered to be small when compared to the distortions that is related to the flexure. So after assumptions, we will see the sign convention. So coming to the first sign convention, that is related to the moments. So here the clockwise moments are considered to be positive and anti-clockwise moments are considered to be negative. So in this beam, if you just see AB beam, so at the A, you're having an anti-clockwise moment, so it is considered as negative. And at B, it is having a clockwise moment, so it is considered as a positive. So MFAB is negative and MFBA is positive. So coming to the next sign convention, second one, it is related to the rotations. So clockwise rotation of a tangent to the elastic curve is considered as positive, and anti-clockwise rotation is a negative rotation. And here in this beam, you can just see there is a elastic curve for AB downward and BC also it is upward. So at A, when we draw a tangent to this elastic curve, so here you are having an clockwise, here you are having a clockwise rotation of theta 1. When we draw a tangent at B, so here you are having a theta 2 at B and a theta 3 at B here. So these two are in the anti-clockwise direction. That means negative. Again at C, when we draw a tangent to the elastic curve and when we draw this rotation, so this rotation is in the clockwise direction. So that means theta 4 is positive. So here we can say that theta 1 and theta 4 are clockwise rotation. So that means it is positive senses. And theta 2 and theta 3 are in the anti-clockwise direction. So that means we can say that these are in the negative senses. So this is related to the rotation sign convention. Now coming to the third sign convention, so related to the settlements. So for example, if we consider this beam AB, so for this A support that is in the left side and this is the B support on the right side. So at B you're having a settlement of delta. So that means delta is considered to be a positive sense for both AB and BA spans. Similar way, when we take AB span, so here at A you're having a settlement of delta. So that is left side support. So this delta is considered to be negative for both AB and BA spans. So this is a sign convention related to the settlements. After this, you are going to derive a relationship for the slope deflection equation. So here you are going to, for deriving this, we are going to consider a span AB, which is shown in the figure. So this is a member of a rigid structure, this AB. So which is subjected to an external loading of W1 and W2, which is having a span of length L. So this is the original shape of a beam. Now we can see that in figure B, so this is a deformed shape of the beam. So this deformation may be taken place with respect to all the displacements. So that displacement can be either translation and rotation. So rotation is theta A at A and theta B at B. And similarly, you're having a delta at B. So here we have considered this theta and delta in the positive senses only. So that means we have taken a clockwise rotation and delta to be positive. And the moments that are developed at A and B also, we consider it to be a clockwise moments only. So that means MAB and MBA are also in the positive direction only. Here we can, our final aim is to find the MAB and MBA relationship in terms of theta and deltas. So coming to this one, our aim is to derive a relationship between the final end moments and the displacement. So that is theta and delta. So for this, our step 1 is to calculate the fixed end moments that due to the given loading condition. So fixed end moments at end A is MFAB. Okay. So here you are going to consider the beam. So in this beam, we are going to same that AB beam only we are taking. So this AB beam is subjected to a external loading of W1 and W2. So here we are considering only the fixity conditions, and due to this external moment, what are the fixed end moments that are developed at A and B? So the moments that are developed at A and B are MFAB and MFBA. So these two also we are considering in the positive senses only. That is in the clockwise direction of the moments. So this is the first step. The first step is calculating the fixed end moments due to the external loading that is coming. And coming to the second step, you're going to calculate the end moments due to the rotations at end A and at end B. Here at end A, so due to this moment M dash AB, so the end rotations are theta A1 and theta B1. So to solve this, you're going to use the conjugate beam method. So when we are applying a moment at A, so here you are having, you have in the conjugate beam method, we are going to draw the bending moment diagram first. So when we apply a moment at this portion A, so our bending moment diagram is M dash AB at this portion, and there is nothing here at B joint, so it is a 0. So this M over EI diagram you are going to draw for the conjugate beam. So this is M dash AB by EI. So for at the support A and support B, if you find the reactions, so those reactions are nothing but your theta A and theta B with respect to A and B points. So now we can see that theta A1 is the reaction at A and theta B1 is the reaction at B. So this one we are going to find out by using a static equilibrium conditions. That is sigma Fi equal to 0. So that means Ra plus Rb will be equal to, so this total external loading, then moment about A equal to 0. So from that you are going to get the one reaction. So two equations and two unknowns you are going to solve. Similar way, when we apply a moment M dash BA, so the rotations are, so the end rotations that are caused due to this moment M dash BA are theta A2 at A point and theta B2 at B point. So as we are developing here moment at B, so our bending moment diagram will be M dash BA at this B point and 0 at this A point. So conjugate beam is nothing but M over EI diagram. So this is M dash BA by EI diagram. So for this, when you find the reactions at A, you are going to get theta A2. When you are going to find the reactions at B, you are going to get theta B2. So now this is the theta A2 and this is theta B2. So by using the static equilibrium conditions, so that is sigma Fi equal to 0 and moment about either A0 or moment about B0. So two equations and two unknowns you can solve and you are going to get theta A2 and theta B2. So after getting these all rotations, so you can rewrite these equations in this way. So here the theta A1 is equal, theta A is nothing but, so here you can see from these figures B, D and E, if you just see, so this B is nothing but it is related to the deformed shape of the beam, and this D is nothing but end rotations due to M dash AB, and this E is nothing but end rotations due to M dash BA. So the theta A is nothing but it is the difference of theta A1 and theta A2, and theta B is nothing but the difference of the theta B2 and theta B1. So after solving these two by making this 2 theta A plus 2 theta B, you are going to simplify this. So finally, the M dash AB will be equal to 2EI by L into 2 theta A plus theta B. And similarly, MBA will be equal to 2EI by L into theta A plus 2 theta B. So by using these two equations are nothing but moments that are developed due to the rotations. Now coming to the step 3. So step 3 is related to the calculation of end moments that are due to the settlement. So these are the end moments that are developed due to the positive settlement, what we considered. So the end moments that are developed due to the settlements are in the anti-clockwise direction, that is 6EI delta by L square. So these derivations are already derived in your fixed beams concept. So that is the reason I am not deriving this equations. So this is due to the effect of settlement in the fixed beam. So when the positive delta is there, you are going to get anti-clockwise directions. The moments are in anti-clockwise direction. So these are the end moments. Now the final step, step 4, that is calculation of end moments. So by using the superposition theorem, the final end moments will be the summation of all moments that are combined. So here we can see that the total end moment will be equal to the fixed end moment, that is due to the external loading that is coming, and the moment due to rotation, and next the moment due to settlement. So the combination of all these are used by using a superposition theorem. So this is going to give the final total end moment. So now you can see that MAB will be equal to MFAB, that is moment developed due to the fixity and external loading, and this 2EI by L into 2 theta A plus theta B is nothing but moment due to rotation, and this 6EI delta by L square is nothing but moment due to the settlement. So this negative is nothing but it is anti-clockwise in direction. These two are in the positive senses. Similar way, you can make it for the BA span also. So that is MFBA. So that is fixed end moment. 2ei by L into 2 theta B plus theta A. So that is moment due to rotation. And 6ei delta by L square. So that is moment due to the settlement. So these two equations are nothing but the slope deflection equations. So this is a derivation of a slope deflection equations. So next, coming to the application part. So using these slope deflection equations, so the rigid joints can be analyzed for the continuous beams without and with settlements, frames without side sway, and frames with the side sway. So these are the application part. And now coming to the procedure. So first, initially, you're going to determine the degree of the freedom. And then you're going to determine the fixed end moments at each end of each span, which are applied loads due to the applied loads acting on the span by considering the each span to be a fixed ended. So here we are going to use the sign conventions, plus or minus. Okay, already whatever we have seen the sign conventions related to the moments, rotations, and settlements. So with respect to that, for the fixed end moments, the clockwise moment to be positive, for the anti-clockwise moment to be a negative. So you're going to use the sign convention. Next, coming to the third one, you're going to express all these end moments in terms of the fixed end moments and then the joint rotations by using a slope deflection equation. Next step is by establishing the simultaneous equations with the joint rotations at the unknowns, you're going to apply the condition that the summation of the moments at the joint should be equal to 0. So by using that, you're going to establish the simultaneous equations. Then you're going to solve for the unknown joint rotations. Then you're going to substitute back the end rotations in the slope deflection equation. Then you're going to compute the moments. Then you're going to draw the free body diagram. So for that free body diagram, you're going to determine all the reactions. Then after finding the reactions, you can draw the shear force diagram, bending moment diagram, and then you can plot the elastic curve also. So this is the entire procedure that you are going to follow for the slope deflection method. These are the sequence of the steps that are going to follow. Now, these are some of the expressions that are used for finding the fixed end moments. So these all are already derived in the fixed beams. So these are with respect to the different loading conditions. So this is the fixed condition only with respect to the point load at the center. The moments developed are WL by 8 at both the ends. So the directions also you can just see. And this is a point load with the eccentric distance. So the moments developed are here. And this is subjected to the UDL, okay, whole UDL. So the moments developed are WL square by 12. And here you can see half UDL. So the moments developed you can see here. And next, this is a moment that is acting in the clockwise direction. So what are the moments that are developed in an eccentric distance? And this is a UVL. So what are the moments that are developed here? And another UVL only, which is linearly varying from B to A. And this is from A to B. So these are some of the expressions that can be directly used for finding the fixed end moments as we discussed in the procedure. Step 2, for finding a fixed end moments, we can directly use these relations. So if it is an anti-clockwise direction, you substitute as negative. If it is in clockwise direction, we substitute as a positive. So in this module, we'll end it up here. So these are some of the referred textbooks that the content has been taken. Thank you.